All right,
Yeah. So
so hello everyone. Welcome to the fourth day of our quantum computing workshop. Um, and Krzysztof, you can start if you're ready.
yeah, thank you. So yeah, today we're going to start with the max cut problem, and by the end of the Friday, hopefully, we will be able to solve the max cut problem using the Grover's algorithm. So, have you had any issues with the today's yesterday's assignment? Do you have any questions about the Grover's algorithm or something else per se? Not really. I don't see anything. Okay, so today we will start with addition, with adding numbers on the quantum computer. And as you will see, this will become very handy once we start to oh, something broke for me. Oh, interesting. Yeah, so once we will start implementing those, we will see that why it is handy, and we will start with half adder, then move on to the full addition, then also do the bipartite graphs, and actually we should maybe start with those, and then once we cover all of those things, then it will be easier for us to understand how max-cut problem works and why do we use the Grover for it. So let's start with a little bit introduction of graphs, what a graph is, and how we define each section of a graph. So, and probably also I should add this tablet for better visibility. Oh, something's not working, unfortunately. I'm sorry for that. And yeah, so the graph has two features. One of them is it has nodes, and the other one is that it has some edges. The nodes or vertices are those circles here, and the edges are the things connecting nodes and edges. And we will use two distinct sets of nodes, and we will color them with blue and red. And this will give us, as I said, two different sets of possible colorings. So the question is, which line can you draw such a line that it cuts the most number of edges that connect with different color? So in this case, and I'm really sorry, but I need my pen right now, and it won't start. So I will delete it and launch it once again. I'm sorry for that inconvenience. But yeah, should work now. Yes, okay. So the question is there a line that if we cut those two edges, what is the number of edges we can cut with a single cut? So in this case, I can draw a single line cutting those two edges. This will be incorrect because here are the same colors. Only this is valid. So for this case, the number is 2. Likewise, we have another graph. And this is kind of, let's say, more interesting because we can arrange the graph in different manner. We can, but we will do it, let's say, later, show you how we can arrange it differently. And for this case, we can draw with a single line, let's say, something like this. So that should, let's say, give us an intuition that we can take, with a single line, we can cut 4 edges. And of course, this would be incorrect because this edge connects to reds. We can also arrange it in somehow different form. And for this purpose, I will call this 0. This I will call 3. Here will be our 1 and 2. and we should connect 0 with 3, 0 with 2, 0 and 1, and 1 with 3, right? Is there anything else? 2 with 3 also, and 1 and 2 are not connected. Right, so once again, maybe color those with red and, well, let's say something like this. And now you can see that we can draw just a straight line that will be cutting those edges. So it turns out that for n number of nodes, right, there are 2 to the n different colorings, right? So depending on how we choose to color those nodes, we will have different answer on how many lines we can cut at once. And this means that this is an NP-hard problem. So we have to check every single coloring to determine which cut will give us the maximum number of cutted edges, right? So we do a cut, and then we count number of edges. This is 1, 2, 3, 4. Then we can use a different coloring with the same graph. And let's say something like this. And we also check how many lines we can cut with connect with a single cut. So it may be something like, I don't know, this, and this, let's say. So maybe 3. Doesn't matter. The fact is, the problem is that we have to check.
Krzysztof,
Yeah.
sorry, to understand the question, the line that you just draw,
Yes.
it cuts also the line which is between the reds. So
Yeah,
this
but let's say we don't count it.
Okay, so we are allowed to draw a line.
Yes.
Which
Because it also depends on how you arrange all the nodes, right? So if I were to, let's say, move this here, this red, right, and connect it here, then you wouldn't have, and connect it also here, then you wouldn't have this issue. Look.
But just to understand the question, I want to understand what is the question really? Like the way that you draw the line in the left plot was like you were going around in the left plot in the original one, right? You were going around instead of cutting the one which connects 0 and 3. So that's why I was not sure if this is by like
is it allowed? Well, it depends on I mean, this is for shortcut, let's say, because you can rearrange this graph to be looking like this one, right? So let's say,
but in both cases, the lines that you draw did not cut the line which connects 0 and
but
3.
look, I rearranged this graph, and it also
but then
does
so that's why I was I wanted to know exactly what is the question. If the question is
the
like
maximum
just draw the line to cut the or like should I avoid cutting the lines that they connect the same colors? But you're saying no.
Not necessarily, yes. Not necessarily, because you can rearrange the graph so that it doesn't cut. Maybe it's not always in all possible manners you can do this, but yeah, the question is how many nodes, how many edges with a single cut you can cross. Yeah, and what is this number, right? So imagine you could rearrange this graph to be something like this, and then you could draw a single line. do we have other possibilities of cuts of the same previous example? Yeah, probably there is. I mean, we can start, maybe if the order didn't matter, we could start from this one. But actually, it doesn't really matter. The question is, we should count how many of those are at maximum, right? So we can also cut in this way, but it is not the maximum number of cuts we can achieve, right? So in this image, it would be equivalent to something like that. So the question is how much what is the maximum number of edges we can cut on a, let's say, uncolored graph. And our task is to color it in such a way, find such a graph that this cut will be maximized, right? This number will be maximized. So it turns out, yeah, that we have 2 to the n different colorings because each node can be either red or blue. So if we have, yes, n nodes, then we have each can be either 0 or 1, right? So therefore we have 2 to the n different possibilities. So the lines are allowed to cut the diagonal, right? Yeah, if you mean this one, yeah, for sure. Yes. Diagonals, whatever. Yes. So we will state this problem somehow differently, and this will be our main goal for today and tomorrow. So for a given graph G, the problem is to determine whether there exists a cut of size at least k. So we should output either true, there exists a cut of, let's say in this case, at least 4, right? 1, 2, 3, 4, or is it there? And the question, if there exists a cut of 5, at least 5, then probably not, because there's at most 5. We can define the problem as find the best division of vertices into 2 groups such that the number of connections between the 2 sets is maximized. Yes, that's also true. But yeah. This also comes down to the fact that in this representation, where you have all the, let's say, colors on the left and all the other colors on the right, then you would just have, yeah, this number of connections. We'll also cover it in a bit later. So a very useful feature of graphs that will, let's say, simplify our problem for now is the feature of bipartite graphs. Bipartite graph is such a graph that there is no connection between the same colors. So only connections with different colors are allowed. So this is an example of bipartite graph where there's no connection between the same colors. And the complete bipartite graph is something where, yeah, as you wrote earlier, it maximizes the connections of such a graph. The question, when we have only one blue node, we won't cut maximum edges, right? So why do we consider that? I'm not sure, what do you mean? Wait, one node we won't you mean in this case? Or I'm not exactly sure what you're, yeah, this one, but one blue node, we won't get maximum edges, right? Yes, we won't, but we consider this, let's say, for educational purposes, right? That this is, in this case, we have only 2 cuts possible, and in this case, we have 4 cuts possible. But let's say we would have to, in order to find for sure what is the maximum number, we would have to check every single combination of colors. We cannot just omit this because there's only like one number of nodes. That in general is not the case. But right now we are focusing on a simple problems, which is bipartite graphs. And we would like to design an algorithm, quantum algorithm, that checks whether the graph is bipartite or not. And the case with bipartite graphs is very simple because the solution of the max cut problem for bipartite graphs is just the number of edges, right? So if I draw a single line, this will give me the number of edges. So 1, 2, 3, 4, 5. And therefore, our solution is very, very simple. And we were first designed the oracle for checking this bipartite graphs to, let's say, have an intuition about what the Grover algorithm for max-cut problem in general might look like. And we also will consider addition and adding numbers onto quantum computer to have better understanding of how this Grover algorithm works in general case. But for now, we're considering a simple case with bipartite graphs. And a complete bipartite graph is such a graph that all the nodes are allowed nodes are connected with no connection between the same colors. So this would also be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Okay, so we will also consider and this is yes.
Sorry, can you repeat the definition of the
bipartite graph? Yes. Yeah. So this is such a graph that only edges with different colors it is such a graph that edges can connect nodes with different colors.
Okay, thank you.
So no connection is allowed here. And for example, this can be example of a graph that is not bipartite, because no matter how I color those, I cannot find a solution, right, such that the nodes are connected, right? So this case is so I cannot find a solution such that the edge connecting two nodes have different colors. Let's say the two nodes, yes, the nodes have different colors. So in each case, no matter how I color it, there will be at least one edge that connects two colors. This is an example of a graph that is not bipartite.
Thank you.
And solution is the number of edges. So in our quantum setup, we will first we will use, say, quantum. We'll use qubits as indication whether a given node is red or blue. If it's blue, then let's say we can call it 0. And if it's 1, we will call it red. Or maybe it's somehow different in the notebooks, but it doesn't matter right now. So we will need n qubits for n nodes. So 1 qubit per node. Okay. So the algorithm looks as follows. So yeah, our task is to find the coloring of a bipartite graph. So we are given a graph, let's say this one, and we are asked to find a coloring such that this graph will be bipartite. And maybe we can work this case manually first. So we know that we can color it in 2 different ways. Let's say if this one is red, then this has to be blue, then this has to be red, and this one has to be also blue. But there's different solutions to this problem. And as you might know, it's very analogous. But in this time, we'll switch the colors. So this one will be red, this one will be blue, this one also will be blue, and this one will be red. So you can see, like, we have 2 equivalent cases, let's say, and for example, if we mark this 0, 1, 2, 3, then we have qubits that will be 0, 1, 0, 1, right? Or maybe I confused it. 0 is blue. Yeah, it should be okay. And in this case, it will be 1, 0, 1, 0. So both of those vectors are actually solutions to our problem. And right now, our task is to design an algorithm that will return those 2 vectors as we want. So the first step is to check colors for the edge. So we know that if a graph is bipartite, both edges should be different. If the graph is not bipartite, the colors of two nodes will be the same. So we will first check for this condition. And we can do this simply by...
Hello. So
Yes.
can you explain the qubits representation with respect to colors? I think it should be 1 0 1 0 no, for the first one, from red to blue, then blue to red, and red to blue, like that, na?
But yeah, I wrote that this qubit should be 0 position. It depends on, yeah, it depends on how you... In this one, I did something like this, right? So Q2, Q3. Yes, yes, but you can also reverse the order. It depends on how you, let's say, read the output, right?
Because at the end it should be only the product between the qubits, na, right?
Why product between those qubits? No, here we have consider such a case that we for qubit 0, we check if it's blue or if it's red. If it's blue, then we use 0. If it's red, we use 1. So we check for the first qubit, first node, it's blue, so we assign it 0, right? The second qubit, 1, is red, we assign it 1. Next qubit, we have 2. Yeah, 2, it is blue, we assign it 0. And the last one, 3, is red, we assign it 1. Yeah, is it correct right now?
Yes, sir. So it depends only on the numbering. It might be changed with respect to individual, right?
So you're assigning 0 or 1 to the nodes and not the edges, right?
Yes, to the
Is
node.
that the confusion?
Yes. To the node. This is, let's say, Q0 is the node, color of the node. Because it's different to say what is the color of the edge if both are
But how
different.
are you getting the sequence though? Like you're going from, are you traversing it through the edges? Like first you go from the red to the blue to the red to the blue.
Well, doesn't matter. It's just the convention of how I let's say label my nodes, right? I can label this as 0 and this one as 1, this one as 2, and as 3. I can also go like this one, this case, right? But it doesn't really matter. It's just how I label it.
Okay, I got it. Yeah.
Yeah. So you're right in the sense that this influences how my circuit is built. But if I choose a labeling and I am consistent with it, I should be able to construct a circuit that that will give my answer to my problem, right? So we know in advance,
you can choose the way how you will do it. I mean, you say that 1 0. Well, you're going from up or down, like here.
From 0, 1, 2, and 3, I labeled them.
Yeah.
But it doesn't really matter.
Okay. So how you want? You can say.
Yes. You can also label this as, let's say, 0, 1, 2, and 3. Doesn't matter. But then this number would be different, right? So in that case, if I label this way, there will not be this one, but this number will be, let's say 0 is 1, so it will be 1, 1, 0, 0, right? So this one is red. This one is also red. Let's say, yeah, it's like 0, 1, 2, 3, right?
So the numbers are very important to write this how it should be.
Yes. But then we also will implement the edges and check for the edges if it's if it's connects to different colors or the same color, right? So, do you have any questions to this coloring? Yeah, go ahead.
So this actually, if we are taking first time, like you have taken numbering the nodes 0101, that is state, right? So can we change in the second that node numbering you have changed 0, 1, 2, 3?
No, because this is like the same equivalent case.
Yeah.
Right?
So if we are, so is it like that if we are numbering the node first time, so in full problem the node numbering will be same?
Once again, I don't understand the question.
Like you have done 0, 1, 2, 3 in the first case where kit is 0, 1, 0, 1, right?
0,
So that
1.
no, not this, the left one.
Yes.
So
So
your
this is also
node numbering is 0, 1 in the left side.
this numbering is this one, right? So okay, maybe I will write once again the same graph, not to confuse it, because I think it causes much confusion. So this one is also coloring of 0, 1, 2, and 3, and this is 0, 1, 2, and 3. But we can also write the same as let's say 0, 1, 2, 3, right? And therefore have something like this. And this, my state right now will be yeah, 0, 1, 2, 3. This will be 0 is red is 1, so 1, 1, 0, 0, right?
So both are equivalent, sir.
Yes, is it fine? Okay.
Yeah, okay, thanks.
Yeah, so this is like the same equivalent graph, equivalent solution, and this is the same solution but different labeling, right? There's a question implementation. Qiskit uses endian notation, right? So in Qiskit it's reversed, so it's Q3, Q2, Q1, and Q0. Yeah, sometimes we will use diff notation, sometimes this. This is how you prepare the oracle. If we're going to, let's say, preparing the oracle is a very broad step, and this is the first implementation step of, let's say, how we would count each node and each qubit. I think node numbering is arbitrary, just how you move through it matters. Yes, exactly, that's true. So right now, we should check for every single edge if this is if it connects the same nodes with the same colors or different colors. And if it's different colors, then we will say it's 1, and if it's not, then it's 0. So once again, we can construct such an edge with color being X and Y. And if the both colors are the same, then we should output X equals Y. So red equals red, then we should output 0. Right? Yes. And if X is different than Y, then we should output 1. So we should flag this state. So let's say consider this case. And I don't know if you have actually implemented the XOR gate with Lydia during this workshop, but yeah, this is just an XOR gate. And this can be done with 2 simple control node rotations. So consider a case where you have first qubit, which is, let's say, value of x, second is the value of y, and third one is the output. Let's call it C, for example. And then we have controlled not rotations, right? Control X gates. And this should give us the gate we're looking for. So we can consider, let's say, 3 different cases. So, or 4 different cases. We start with state 0, 0. Then this is, which means blue, blue, and the output stays the same. So, yeah, so it is 0, 0, and then third qubit is also 0. Second case is 0, 1, 1, and then let's say first C0, it doesn't do anything, so 0, 1, but the second C0 changes this. Let's say this is applied, this C0 is applied from this to this, changes the value of the third qubit to 1. You see, so yeah. So we can confirm that actually we have 2 different colors, which is blue and red. And likewise, we have state 1, 0. This should be 0, actually, I'm sorry. This should be also 0. So it is consistent. So the first C0 is here and it does nothing because it's 0. And in this case, the first C0 changes the output from 1 to 1 and also leave this as 0. And then we have, oh, no. Sorry, not like this, but like, but this changes, this changes.
Yeah, it will be 1.
Yes.
And previous one as well.
Yeah, this should be 1, right? But then we apply next CNOT gate and it stays the same. So, yeah, it's actually correct. 0. I was afraid it will break. 1. Yes. Perfect. Thank you. So once again, we have red and blue. And the last case is that 1, 1, we also apply it to 0. First CNOT changes the second qubit to 1. And then second, this should be also 1, sorry. And the second CNOT also changes the third qubit, which will then be 0. Yeah, so we can confirm that our state is exactly what we wanted, right? This is 0 as we expected. Okay, so first step is behind us. Check colors for each edge. So if we know that if 2 nodes, X and Y, are connected with an edge, we should use a third qubit, which will flag if those 2 nodes are the same colors or different colors. Yeah. So check colors for each edge, check if all edges are 1. So right now we have, let's say, made a very simple case, but now let's consider what happens when we add more nodes and more edges. So I will create a simple circuit and once again do the following graph, which would be 0. And actually, maybe this time I will change, let me just quickly see the numbering so that it is consistent with the notebooks. And we will go to QNickel, content, and search for Max QPoland and bar pi type graphs. Okay. And I will first edge checking. Yes. Use such a numbering. So 0, 1, 2, 3. And this is for the purpose of being consistent with the notebooks, right? So, okay, we have qubit for 0, 1, 2, and 3. And we will do such a thing to connect those. We can also maybe label the edges. So we will label edge with A, B, and C. A, B, and C. So it doesn't confuse you. So first we check for A. So we connect 0 qubit with the second qubit. Okay, so 0 qubit to the A, and second qubit also to the A. Okay, then check for B. So,
sorry, what do you mean by connect in terms of circuit?
Yes, so we designed a simple XOR gate for given X and Y nodes, and then we check if the connection between X and Y, right? This connection C is, let's say, if this connection between those two nodes have the same colors or different colors.
Yeah,
right?
but like here, when you connect, you use CNOT gate, right? XOR.
Yes.
So, but what do you mean by connecting X to an edge in the second
X to Y.
No, but
I mean,
in the new circuit,
Yeah.
like here, what do you mean by connecting 0 to A and
No, if I said that, that's a mistake. Yeah. So once again, look at this graph. So we have X and Y, which are 2 qubits, and the connection is labeled as C, right?
Mhm.
So we flag if this C is 0 or 1. If both nodes are the same colors, then it's 0. If they're different colors, then value of C should be equal to 1.
Okay. So, but then in the below, so here, okay, here is also these are like C, these are XOR, right?
Yeah. It's
Yeah. Okay.
maybe
Okay. Now
it's
it's clear. Yeah, it's
this implementation, this notation is the same as this, right?
no,
Yeah. So
I was not sure about the drawing.
yeah, this is
Sorry.
the simplification. Yeah, this is actually equivalent.
Okay.
These are the same gates.
Hmm.
So yeah, we'll say we will label edge A, check if it is, let's say, if they have the same coloring or different coloring. And we will have
we
to
know which nodes are connected. Priori, we
Yes,
know which
yes.
nodes are connected.
Yes.
Okay.
Yes. We are given a graph, right? So we should know which nodes are connected. And we could also check if, we'll implement the same for B. So 1, 2 with B. So 1, 2 to B. And last step, 1, 3 to C. 1 and 3 should be connected to C. Okay, great. Yeah, so now we have an flag for each of those edges. There's a question. I think it is shown as a simplified representation of what nodes are connected by which edges, so we can transverse through each edge and see all the nodes in that edge or are different colors. Yeah, basically, I think you're correct. So we have a label for each edge, and we have a condition that if a graph is bipartite, all the edges must connect different colorings. So we should observe, if a graph is bipartite, we should observe that all three A and B and C are flagged as 1, right? So that confirms that if they are flagged as 1, that two nodes have different colors. But if for some reason one is different than bipartite, but if for some reason some is different than 1 or is equal to 0, or B is equal to 0 or C is equal to 0, then we know that this is not bipartite. Okay. So what is the logic gate that, can you tell me or write in chat, that we can use to check, let's say this will be our O as output. Which logic gate can sense or check if all those three A, B, and C are ones? CCX, yes, exactly. So we should add a NOT gate, which is controlled by all of those A, B, and C. The Foley gate, yeah, exactly. And now comes the fun part. So we have successfully flagged, let's say, a output. And if this output bit is, maybe O is not a good label, I'm sorry, because it may be mistaken with, yeah, and also, yeah, it may be mistaken with with 0. So I don't know, which should I use? Maybe let's say, or let's say P for some reason. If this P is 0, then we know that this is not bipartite. But if this P is 1, then it is. So now we will use a Grover algorithm to flag, change a face of this P qubit. If it's 0, then do nothing. If it's 1, then we should change the face of this. And we can do this simply by applying a Z gate. So this, in this case, so if P is 0, then our state will be left unchanged. And if P is 1, then we will change this flag to -1. And you can already probably see the connections to the Grover algorithm, right? We also had this phase flip, the oracle of changing the phase of our desired output. But right now we have a giant, let's say, matrix with all those qubits being in different superpositions, right? And this matrix in general, for all of those qubits, will have all the entries non-zero. Maybe, yeah, if all of those are in superposition, as we will see later, then they are not 0. So let's say A11, A12, A1N, right? And also AN1, A and N. But as you probably remember, for a Grover operator, we need a matrix that looks in the form of ones. Somewhere here, maybe -1, which is our key we are searching for, right? And others should be 0. So in order to do that, we just have to do the same computation as here, but reverse it. So that if we know that we are starting from 0 here, right, then we should also leave the state unchanged. So I don't know if I will be managed to copy this actually, but it'll be different to later than, yeah, let's see what happens. My computer thinks. So in the meantime, I can answer the question, what's the use of phase flip here? Does it serve a purpose or is it just mathematical convenience? Yes, it serves a purpose. It serves the purpose of, let's say, implementing a Grover oracle. Yesterday, we had an oracle which consisted of simply 2 or multiple controlled z-gates, but now we constructed a huge oracle which checks for every single condition of edges, and then at the end, it applies a phase flip if all those conditions are met, or does not if this condition is not met, right? So yeah, I think it broke, and I think it also my notes are broke. No, it's not. So in order to do that, we would like to take this circuit and do the reverse computation, reverse it, so that we have a circuit that leaves the state of those qubits unchanged, but changes the phase of this P. And actually, for the exact matrix representation, this would, I think, look like more like 1 minus 1 and one's here. And why is that? So the first, as you remember, is 0, 0, 0. And I have to count it right now. 0, like 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 qubits, which is a lot. 5, 6, 7, 8. And this is, let's say, our 0 state. And 0, 0, 0, 0, 0, 0, 0, 1, which is our, let's say, flagged state. Or actually all the states that are, yeah, so this last qubit is the P1, is the P1, and it should have its phase changed to minus, let's say, 1, right? And I think, yeah, since this is P and there are probably more of those P's here, then we should also have this in some more cases. So maybe it is not really correct. But all in all, yeah, this should have ones, minus ones. This matrix should have minus ones, where all the conditions of a bipartite graph are met. So actually, our search keys, yeah, you remember those keys I wrote yesterday. So they are the solutions of a graph being bipartite or not. Yeah, so I think this is all for the theory for now. Yeah, it's took a long time, but now we can move on to the implementation of Grover algorithm. And the question for you is, maybe do you need a 5-minute break or not necessarily? Yes, break. Yeah, okay. So we will have 5-minute break, and then we will move on to the implementation of Grover algorithm. However, for the Grover algorithm for the bipartite graph, but we have covered in theory a lot of today, so just executing goes will be fast. So see you at maybe, let's say, 8 in 6 minutes to the round hour. Yeah. Okay, so I hope you're there. Let me know if you're back from a break or not, really. If not, then we can wait a second for mother to come back. Okay, so I see that Assam is back, so I hope that others are too. You can also write in chat if you're back or not. Let's see. But yeah, so we're back at the notebooks. And first thing I wanted to show you is, let's say, how you can construct your own circuits and your own gates in Circ. I will just use it as a visualization tool. So this will be equivalent to Cascade Barrier because I couldn't find any similar equivalent in Circ. But yeah, this is only to print those dashes when I need them for the circuit diagram. Yeah. So yeah, we have covered during the theory section all of this. So, sorry. Okay. So yeah, we have set the max cut problem, which is partitioning the vertices of the graph into two distinct sets, which we named the coloring and a cut, and the number of edges between the two sets is maximized. But yeah, we also have a different formulation of the same problem with the size of at least k. And yeah, we've covered a very simple case with bipartite graphs, which are and which are not. And we will continue by checking the bipartiteness, let's say. And the first one task is to implement the idea we were checking before. So you should write a code to assign each of those vertices be even 1 or 0. And as you can probably remember, you can go from change the state from a 0 to 1 using an X gate. So maybe I will give 2 minutes for this problem because I think it's rather simple. And yeah, we don't. Should we always import all gates? Yeah, you should import all the gates you're going to use. So in this case, we're going to use X and I, but I think you can also do it very conveniently. So import this one, and you should all have all the gates available also by the default. But yeah. Or you could equivalently, if you don't want to import them, you can also probably write circ. Oh, I don't have it here. Let's say circ dot Yeah, but then you would have to use the circ and the gate every time before every gate, so it's not that convenient. But yeah. Okay, so are you ready or not really? Yeah, more or less. So yeah, as we wrote earlier, it is sufficient to just apply an X gate, so we can do append, and we would like to append an X gate to the, let's say, if result is 0, then it is red. So red should be 0. The other way, as I wrote in the notebook, but it doesn't matter. And blue should be 1. So we should append an X gate to qubit 1, and also and this is dot append also X gate to 2 second qubit. We should check the output. Yes, so qubit 0 is red. Yes, it is. Qubit 1 is blue. Yes, it is. Qubit 2 is also blue. Yes, and qubit 3 is red. That's true. Maybe I'll also enlarge it so you could see better. Yeah, so this is our circuit, our result. Now we're going to check the edges as we spoke earlier. So yeah, we will implement this XOR gate, which will be just double CNOT gates. Let's see what this happens. Yeah, this is how this circuit should look, and this is what I also was showing and drawing for you. And we can now verify the correctness of this circuit by running a loop where we will change A to 0 and 1, and also B to 0 and 1. So we will see. So yeah, we have a very simple, let's say, 2-edge graph, and first vertex is 0, and the second vertex is also 0. Then the output is 0, where if the vertices have different colors, then the output is 1. Likewise, in this scenario, also 1. And at last, if those two have the same color, so they're both 1s, then the output is 0. So yeah, right now we're going to design an oracle for checking bipartiteness. Sorry. And as I said at the beginning, we will use an X operator to check for the value of an edge. We will then use multiple controlled CNOT gate to check the value of all the edges if they are 1. And yeah, this is task for you. For graph below, implement the first 2 steps of an oracle described above. The first 4 qubits are for vertices, the next 3 are just for edges, the last qubit is for output. Last qubit should be in state 0 if the coloring of vertex is correct. So I will give you maybe also 2-3 minutes for this. Do you want me to show you the circuit I wrote before, or not really? Okay, so I will display it, and if someone wants to do this on their own, then feel free to do so. So I think this should be the correct coloring, the correct implementation. So maybe I will write also the qubits. So this is numbers. Let's say qubit 0, 1, 2, 3, 4, 5, 6, 7.
Just to clarify, Krzysztof, here in the task, you set 0 and 1 to be blue. All right. I mean, you change the colors for 0 and 1. Not here in the task, right? So
the colors, yeah. Here you mean, right?
Yes. No. In the task that you are waiting for us to do, if you go down,
Yes.
down.
Okay. All right. Yeah. I see what you mean. Yeah.
So you because if you go to the task, go a bit lower. It's like you start the 0, like you change the state from 0 to 1 on 0 and 1 qubit. In the 0th and the first. So it's like simpler than the previous task. I mean, it's fixed. We are not looping over the different combinations.
I mean, I would say it's extending the previous. I mean, it's extending the task 1 from this one. Yeah, should color those, right? So we assume that now we have
fixed coloring, and now we don't change the colors in the second, like in the previous task, we were changing the colors of these two nodes, and we were checking if we are bipart or not. Here, it's like a fixed.
No. In the first task, we were only asked to change the colors. Here
No, I mean, if you go a bit up.
Yes.
Here we are changing the nodes, and we are checking if the graph is bipart or not. So we don't do this. We will have a fixed graph, and we just want to check if it is bipart or not.
Yes.
Okay. Yeah.
Yes. So we assume that we now know the coloring, but as you may guess, using Hadamard gates, we can put the graph in a superposition of all the possible colorings.
Yeah.
But it's like the next, let's say, step. So are you ready, let's say, or more or less, or do you need more time? One minute more, sure. So I will display maybe, in the meantime, I will copy paste my line for a barrier for you to see and print it. And once again, this is the correct, let's say, code we're trying to implement here. So I think we can continue with the implementation. So I will just copy paste the solution for now because it'll be easier, but I will go step by step on what it actually does. So let's say I will add those visual barriers for you to visualize, and measurement, let's say, at the end, and we'll print the circuits. So yeah, we have, let's say, we have I'm not sure why this is so. Because I have already, printed it, so sorry. Yeah, so the measure output is 0, and we have incorrect coloring. Why is that? That should not be the case, actually. We should have correct coloring. Because of course I forgot to check all the gates. So now it should be okay. Yeah, so we have first 4 qubits assigned to each node, Then the next 3 qubits are assigned for checking the edges, and the last qubit is checking for all the edges. So qubit 0 is blue, qubit 1 is also blue because of those X gates. We are checking if they're this, this is the case. And now we're checking if 0 and 1, and so 0 and 2, which are connected, we're checking if they have the same coloring or not. Likewise with 0 and 3, and also 1 and 3. Yeah, so 0 and 3 and 1 and 3. We're checking for those graphs. And at the end, we're executing a multi-controlled X gate to see if it is correct. So yeah, measurement output is 1, and we can confirm that the graph is bipartite. But on the other hand, if we do the incorrect coloring, so append maybe also this gate here. So this will be more convenient if we also do it like this, right? So do single X gate. We can see that, yeah, the output is 0. So we're taking more and more edges and combining them into bigger chunks of code. Yeah, and the 2 next stages are the
any reason that we do the measurement on all qubits, not only on the 7th?
Right now, not really.
Okay.
Because look, we are also fetching the result of only the last qubit. So for now, there's no reason to do it. Yeah. Yes. So the remaining steps of the oracle, as I said, is the phase flip of the state 1 if it's an output. And the last one is actually we want all the measurements of the first qubits to be the same as before as the oracle. So therefore, we would need to reverse the computation to arrive at the state before. So therefore, it will give us like this diagonal matrix in which only the -1 is where this last qubit should be. Yeah. So now we have, let's say, more complicated code, and now we have our oracle. And oracle computation will consist of oracle, which is just the code here we wrote, the Z gate, which I said at the beginning, and the inverse oracle. And we can visualize this as follows, right? So we first initialize the graph and all of the possible superpositions of all the states. We then have an oracle which all those steps are checking if a graph in a given graph is bipartite or not, then changes the phase and reverses the computation of checking this condition.
What do you mean by reverse?
I mean, reverse is you reverse the order of computation.
But
so
is it but isn't it like like if I think about it as a matrix form, it's not the inverse of the matrix?
Yes,
so
it is.
So only because these operators are
conjugate.
Self-conjugate, then because of that. No, they're not self-conjugate. Like they are not nilpotent. So the square of each of them is 1, basically. That's why if you apply 2 of them,
it's not that, I would say. Yeah, the inverse is just if you have a unitary matrix, the inverse of that matrix is just U equals -1, right?
Yeah, but in terms of the gates,
yes,
the inverse of CCCX is CCCX.
Yes.
So which means U -1 is U.
Yeah. This is the definition of the unitary gate, actually.
Or other words, U square is 1.
It's not it's it should
because
be
u times u times u minus 1.
yeah,
U
but
times u
actually
inverse is 1.
it's I will have to check. Now the condition of a gate being unitary is no, sorry. This is for the special case of the CCX gate. But this is not in general. In general,
here, like just because these operators have this property that they are equal to their inverse,
yes.
like Hadamard.
Yes.
So, like, if we apply twice, we get identity matrix, basically.
No, it is like when you apply this dagger. Yeah. This case particular, right. Yeah, you're right. Sorry. But in general, it is not the case. That's why I was confused a little bit, and I was like not sure what you're talking about. But yeah, in this case, yes, applying this twice is just equal to the one matrix. But in general, it's that like the unitary is that U dagger, right? U dagger equals U. No, this is Hermitian matrix. U dagger equals U to the minus 1. This is unitary matrix. There are different names. But if we
now
convert
in
this,
Circ, when you use this reverse,
yes.
So what does this reverse do really? I mean,
so there are two. If the gate, as you said, is self-inverse, as in the CX gate, it just repeats it, but it reverses the order of the gates, right? So here we have, let's say, mirror image of the gates. So here we have applying from 0, 4, right? Then 0, 5, and 1, 5, let's say. But here the order of the gates is reversed.
so only the reverse, it's not the inverse. That's my question.
Yes, it's always there. It's also their inverse. So because in this case, the controlled NOT gates are also their their inverse is the same as the gate. So because the equation is, let's say, this equation is satisfied, right? We apply the same gate, but we also reverse the order of application of those gates. So maybe I will do something like this. Take a screenshot and then paste it here so we can draw it. So if I have gates that I apply in the order of 1, 2, 3, 4, 5, 6, 7, then I should do, in order to apply, let's say, an inverse of those section. So this is U, and this is my, let's say, okay, this is my U to the minus 1. Actually, it should be, yeah, U to the minus 1, or this should also equal U transpose. I mean, it's Hermitian conjugate, but yeah, we can do this by simply first reversing the, I'm sorry.
It should be a bit.
Should be with this gate here as well. Yeah.
But my question was if this syntax reverse is just reverse the order of operators, or it takes into account that, so it's the inverse really.
This inverse is inverse.
So it is inverse, not reverse. Okay. So if it's inverse, then it's clear.
Yeah, in order, sorry for the confusion. In order to compute the inverse of a gate, we have to do two things: compute the inverse of individual gates and apply them in reverse order. Yeah? Okay, yeah, sure. Thank you for that.
Thank you.
So right now you can see that with the following output, some states are labeled with those minus here. And you can see that these states are 0, 0, 1, 1 and 1, 1, 0, 0, right? So if we go back to our graph, which is here, we will see that 0, both of those edges should be colored the same color. And likewise, 2 and 3 should also be colored with the same color, with the same, same color. So therefore, we have successfully created a Grover operator that flips the sign of our desired circuit, of our desired keys. Yeah, there are some questions in the chat. Reversing returns the previous values which were in the beginning. Yeah, but with a phase flip. Somehow resetting qubits to reuse. Exactly, right. So we can consider gates as matrix. So we take inverse of these matrices and they act on it in the opposite order. Yes, exactly. So exactly as I showed you here, this is the, let's say, inverse. If we consider this as a matrix, right, then this would be the inverse of that matrix. And in order to do so, we have to take the inverse of this individual gate. So this will be CX inverse, and also reverse the order of applying those gates. Okay, so
it seems that Cirque in this sense is like more advanced compared to Qiskit, right? So there we need to build our inverse, like in general. So like using this inverse, it does everything for you. You don't need to think about implement. So here in this case, it's simple. We know that all of these operators, we can just use the same because they are equal to their own inverse, right? But for more complicated gates, if I have sequence of gates, or even for one gate, thinking about what was the inverse of that gate that you want to implement.
Yeah, that's true. But I think that Qiskit also has, this code somewhere. I think
so
it's
the inverse.
Yes, I think they also have the inverse.
And what about the controls? Like the couple of controls?
For sure.
Okay.
You also can create a function like this, and you also can create
no,
just
but like control with few control gates. We can have it also in Qiskit?
Yes.
Okay. So
I think so. But for now, I don't remember the exact syntax. I'm sorry.
Okay.
But definitely, I'm pretty sure that both of those gates are available in Qiskit as well, the inverse as well as the multi-control gate. Right. So back to our Grover, we have successfully labeled our correct states with the minus sign. So now we have to just implement the Grover, and then we should be fine. So the Grover consists of, as remember, the Grover, the oracle, which we have computed, and the Grover diffusion operator. Now we will probably go to this diffusion operator. Yeah. And here we have also, like, if we know that there are two possible colorings, how many times we should execute our circuit. So maybe 5 minutes for you to complete the codes. And you can take the oracle and the oracle computation just from this code here, right? You can also create a custom function. Maybe I can show this to you, which is just edge check, because that will be easier for you to just check those edges and not necessarily write this all over place. So 5 minutes for that. So maybe 2 more minutes if you need. Are you finished more or less? Do you need more time? Yeah, more or less. Okay, thank you. So yeah, let's say since our code is, yeah, I'll give you this edge check. We can do the same with now yield and edge check, and we can do the edge check for all the edges. So 0, 2, 0, 3, 1, 2, and 1, 3, 0, 2, 0, 3, 1, 2, and 1, 3. Yes. And check all the edges, controlled. Oracle will be simply yield oracle yield this z gate on qubit, last qubit, which is qubit 8. Then inverse of oracle. Okay, so let's see. This should be this one, right? But this, of course, doesn't tell us anything. So I will go and ahead and copy the print circuit. And also, probably, we would also like to, yeah, this is kind of messy and ugly. I will show you for now only the solution with one Grover operator. We will also use those, where I have it, those barriers. So you can actually verify that this is, yeah. Here I had some barriers, probably. This is the barrier, okay. Yeah, so going back to our problem, which is here, we will use the following. We will definitely put an here, and also, yeah, here, let's say here, maybe also after the Grover diffusion operator. Or maybe not. Okay, let's see how this looks. And this looks better, but not perfect. So,
sorry.
yeah.
In definition of oracle and oracle computation, shouldn't we reverse? So the oracle,
like this one, you mean, or?
No. The order doesn't matter, but the oracle computation is what you like previously. What like in the previous.
Yeah, sure.
So this is building the oracle, right?
Yeah. I was looking at this solution, and yeah, thank you so much for it. Yes, of course. Yes.
Now we compute it.
Yeah, that's right. I thank you so much. But yeah. No, it's not. Wait, let's see a second. Compute Oracle. Edge check. Oracle computation, global diffusion, Oracle computation. The one previously looked a lot better, I think. Because maybe now it's just too many barriers. So maybe let's get rid of this measurement. Does it look better now? Sorry, we just need to print it. Yeah, okay. So we can go step by step right now, I think. So we have first checking the edges, right? Those blocks are checking the edges. Then we have checking if all of those edges are actually one, the conditions are actually one. Then we apply the Z. Then we apply the inverse of those computations. And then we apply the Grover diffusion operator. Maybe I will add one more visual barrier so you can see this more clearly. And the Grover, no, that's not what I meant. Oh, well, yes, okay, maybe. So as you remember from last time, in order to do this Grover diffusion, we need Hadamard gates, X gate, controlled Z gate, and this is only done for the state that actually, let's say, uses our Hadamards. So actually the qubits we would like to solve. This, to actually the keys we would like to find. And yeah, again, followed by series of X gate and Hadamard gates as we implemented it yesterday. So I will go back to this. Why Hadamard 8 for edge qubits? Well, because we have also this Z operator here, right? So it should be applied to all of the oracles in order to get this value, right? Because the Z here flips the face of all the colorings that are correct, but in order to capture it, we also need to apply those Hadamard gates to every single gate. Yeah, sometimes it's very confusing, but once you, let's say, try to implement it yourself and let's say drop those Hadamards and X gates, then you will see some different, let's say, anomalies. And once you, let's say, consider the linear algebra and matrices behind them, it will be very clear why you should do this. But let's say intuitively, the superposition of this face is somehow kicked back to all of the qubits before. So that's why, let's say, intuitively you would need to put Hadamards on all of those qubits. But since the state you're looking for, the keys, are actually stored in the first 4 qubits, that's why you only need the Z operator for those only first qubits. Let's say intuitively we can think of it like that, but actually in order to be very specific, we would like to need to trace all of the linear algebra that sits behind it. So we can, for now, we can take this oracle as for granted. So let's print the counts, and maybe I won't print the circuit because it is now will be too large for us. And also we were said we should apply this Grover operator twice. So let's see what happens now. And also I don't want to print it. Okay. So right now the most prominent examples, let's say, and here, as you can see, we apply the measurement to only those 4 qubits first. So therefore, we measure only the states we're interested in, the colorings we're interested in. And you can see that we have one output that is 0011 and other that is 1100. And this corresponds once again to the correct coloring, which is, let's say, both are both are blue or both are red. You have any questions? Do you need to take a moment to consider it once again? Yeah. So that's now the task 4 is to repeat the task 4 for the following graph. And as you can see, this one is not necessarily bipartite. And the question is, does the graph has any correct colorings or not? We know in advance that there is not any correct coloring because this graph is not bipartite. But could you say in advance of the frequencies of the outcomes? Yeah, just question for you. You can write in chat, and you can have like maybe also 3 to 5 minutes to consider it. All right. So I'll give you five minutes to implement it. Okay. Are you more or less? Could you please copy the syntax to plot the barrier? Yes, I can copy this. So this is all coloring are, oh, maybe I can do this somehow. Oh, I can, one second, I can pass you the code right now. Yes, and then you have to do yield or apply. But I haven't, let's say something like that. Okay, I've sent the chat the code to plot the barrier, but yeah, let's say we go back to this one, and let me just quickly copy the solution. Yeah, we do the same. So edge checking and so on and so on. But now we see that, as you correctly mentioned, all have equal probabilities. What does it mean? It means that the Grover algorithm didn't find any reasonable key, right? So we started in a superposition, but it didn't find any key. It didn't find any, let's say, value to flip. So therefore, it just, let's say, returned the balanced state as it was provided to the algorithm. Yeah. Do you have any questions regarding this? So yeah, actually, it turns out that all of those steps we were trying to do to determine whether the graph is bipartite or not, we can do this in, let's say, yeah, O and to the n steps, and this is the number of nodes. But it turns out that, let's say, yeah, classically we can do this 2 to the squared times. So classically it's better, I think. Yeah. So all this mathematical and groundwork was to then solve the actual max cut problem and understand better how the actual max cut problem, which is for general graphs, not only bipartite, so how this oracle might work. So this is just, say, pre-computation. Are all non-bipartite graphs leading the equal probability? For this, yes, because the Grover algorithm checks for the key. It doesn't find any key, so it doesn't apply a phase flip. So therefore, it returns the state as it was. Yeah. So yes, answering your questions, all non-bipartite graphs will lead the equal probability. Do you have any question to this? Because we'll start a new notebook.
Just out of curiosity,
Yes.
is it like related to any like well-known math or physics problem? This, or it's just educational?
I'm not sure, to be honest. I haven't. I'm to be honest, I'm not really that good at graphs. They're not my main interest. Right? So it's hard to say if it's a known problem. For sure, you can hear about traveling salesman problem and how you can optimize it on quantum computers. But I would not go into very much details because I'm not familiar with this problem myself. I haven't, let's say, go through it myself, but there are different algorithms. Probably, maybe Grover, maybe also used, but I'm not sure, to be honest. I wouldn't like to mislead you in this case, but for sure, traveling salesman problem is something that you can tackle on quantum computers. Yeah. Okay. Would you like to have, let's say, 7-minute break to 9 o'clock Polish time? And then we will go to what? Anderson number checking. Yeah. So let's meet in 5 minutes because I assume that you may also be quite tired after already spending 2 hours almost. Hi, are you back? Hope so. Yeah, I can always count on you. Okay, so now we're going to go to others, and we'll do first half others, then others, full others, and then number checking, and so on and so forth. Why we would need that? So we previously we defined our problem as to determine whether there exists a cut of size at least k. So as you may think, we would like to add those cases where the cut exists. And then if it does exist, then we should check if it is definitely at least k. So that's why we need those, this number checking to be sure to solve the max cut problem correctly. Okay. So first the other. So the half adder is such a, let's say, construction that we have two bits, A and B, and let's say it's kind of a XOR gate, but in a case where, let's say, two qubits are 0, the, let's say, 0 plus 0 should give us, let's say, 0, right? And 0 plus 1 should give us 1. 1 plus 0 should also give us 1, but 1 plus 1 in decimal, this should give us 2, right? But in binary, it's 1, 0. So we have two additional bits that you need to have in order to store the resulting number of the addition. So in this truth table, A and B, we have, if both are 0, 0, then C is the carry register, we call it, and the sigma is the sum. So if both A and B are ones, then the sum of them is 0. Let's say in this XOR gate is 0, but we also have an additional carry out, which indicates that we have, let's say, an overflow of bits. And this can be implemented with the following circuit. So we will check in each case, verify if this circuit actually achieves our goal. So let's do it like this. We will, and now we will use little endian numbering. So first is Q1, and then it will be Q0. But then I will use Q, should be, I think, oh, we will see later. I think it should be Q2 and Q3. But I'm not sure right now. Yes, I think this should be it. So if both are 0, then the first CX, and we will start also with initialize those 2 qubits as zeros. Then the first control not gate does nothing, and basically we leave the state unchanged. So 0, 0, back to 0, 0, right? What if we have now case with 0, 1? Well, if we have that case, then still this does not have any effect because both bits have to be 1. But now we have the effect of the first C0, right? Which is applied to qubit 0. So then qubit 3 will be changed. So this will be 1, 0, 1, right? So we can see that this is, this should be 0, 1 and 0, 1. And this is, of course, 0, 0. Right? If you have any doubts, then feel free to interrupt me and explain once again. 0, 1, 0, 1. Yes. And now we have 1, 0. Also initialize the second reserve C0. But now, look, once again, the first one is not changed because both have to be 1. But then Q1 is 1, so we should activate this control not gate to the qubit 3. So we should once again have qubit 3 is this one, so we should flip this to 1. And at the end, we have case where this is 1, 1, and again do this. So what do we have? 1, 1. Yeah, but this time the first CNOT gets activated. So it maps the first qubit changes to 1. So it's 1, 0, right? But then also both CNOTs activate the last qubit. So actually, because we have 2 CNOTs, it actually remains in the 0 state. So we have 1, 1, 1, 0. Yeah, and you can now see the resemblance of the table here. So maybe I can copy it and display it here. Also, that when we have basically the output is what we would like it to be, right? You can clearly see the resemblance of both. So yeah, we can verify that this is in fact correct. So we have, let's say, successfully created a circuit where the number C, which is constructed from Q2 and Q3, is actually being implemented onto as adding bits A plus bits B. And maybe right now we can go to platform to see the implementation of the codes. Maybe some task will be also there. So yeah, first I will go with this circ and the chosen kernel, right? The barrier. And yeah, this is the circuit I was talking about. So right now you have the task to implement the above half adder and verify that this is indeed correct. So your only job is to apply one multi-controlled NOT gate and 2 single CNOT gates. And maybe I think 2 minutes should be enough for that.
Sorry, Krzysztof.
Yes.
In this loop, in this for loop, for input in this, like, no, I mean, just when we want to execute the for loop, it's
Yes.
for, but usually we have like for I in blah blah, but how does it look
Yeah.
here? This I mean the syntax, the loop syntax, how does it?
Yes. You mean the Python strictly, not necessarily circ, right?
Yeah.
So if you do this, you will see, oh, something is wrong. Sorry, input. Yeah. So it just
okay, so it's like for
over
I
the list.
in. So I thought that input has like a special thing. It's just a parameter.
No, it's this, yeah, for
Just-
the input of the circuit, let's say. Yeah.
Yeah, but like because it changed the color to green, I thought that maybe
You know what? Yeah, because there's also there's also like a function in Python input. There's also this input function. I'm not remember the syntax exactly, but
yeah, but
let's say
input is
there's
not the
also the
best.
function.
Input
So
is
that's
not the
why
best
it's not.
variable to be used, right?
Yes, yes, yes,
Okay.
yes. Let's make if you let's say inputs, then yeah, thank you for that. Okay, are you ready? Let's say it indexes the character. Yeah, for sure. So we can go through the solution, and the solution is actually very simple, and it is just appending three gates. Append Control X and 2 times append. So let's now run the circuit and verify that, yeah, indeed, we have added bit 0, 0, sum is 0, count is 1, or this carry bit is 0. Sum is 1, count 0, sum 1, count 0, sum 0, count 1 for the case where you have both bits. Yeah, perfect. And now we will implement the, so far we have implemented the A plus B, but now we would like to implement an in-place operation, in-place addition. Why this is so? Well, you know that qubits are likely, quantum computers are likely constrained from the amount of qubits they can have. So we would like to shrink maximally the number of qubits, and we can therefore implement the in-place addition. So we have a register that stores, for example, number 2, but after those two gates, the, let's say, purpose of those registers will change. So now the 1 will be the carry, and the 2 will be the sum after the operation. So it may be confusing. But for now, we will just go ahead and take this circuit. I think I have, yes, written in here. And we will go through every single possible state to verify what is actually the case with this. So we will do this maybe in the same convention as the notebook has, so not to confuse it. So Q0, Q1, Q2. So we'll now use big endian notation. Q0, maybe let's do this here. Q0, Q1, Q2. And let's see. So 0, 0, 0. This should give us the state. Both are 0. So yeah, this should be left unchanged. 0, 0, 0. 0, 0, 1. What about this one? Maybe not. Because we will first consider cases where this Q2 is 0. So maybe this one. Yeah. So what happens here? Here we have multiple control X gate. So not both are 0. Only and also the 0 is also unchanged. So we should do this one, right? Because the 0 qubit which controls all of them does not change. Again, now 0, 0. Now, not both are not 0, but here we have control not activated, so we have 1, 1, 0. And the last case is 1, 1, 0, which will be activating the last qubit. And actually, this one will also flip the state, so it will be 0, 1, 1. Am I right? No, no, I'm not. This should be
Okay.
reversed.
Yeah.
And what those qubits actually mean. So before, let's say, the addition, let's say this plus equals operator, we have different bits, A, B, and let's say this carry. But now Q0, let's say, is Q1 is, let's say, meaningless. So we will assign it, leave it as A because it stays unchanged. But now our qubit 2 will be the carry and our Q1 will be the sum. So this is the sigma. So let's rewrite this in a sense that we have changed the number here because it'll be easier. So we change the meaning of those states. So let's verify this like this: 0, 0, 0, 0, 0, 1, and also draw a line here: 1, 1, 1, 0, and 0, 1. No, I messed it, sorry. 0, 1, 1, 0. And now you will see that we have successfully implemented this addition. So 0 plus 0 is 0. Now we have to, like, let's say, look at from two different perspectives. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2 in binary, right? This is, yeah, equivalent of 2. So this is like very, let's say, tricky because we then change this bit B becomes the sum, and we also need to inverse, let's say, the order in order to, let's say, see the resemblance of actually adding those two numbers, right? So that's why it might be a little confusing. But this is not the end of the story because we have 4 more states to consider. But since we don't have that much time, I think I will just pose the solution of this. So again, we have I'm sorry for that. Yeah. Yeah. What happened? Oh, I deleted it. Sorry. So yeah, we again have input and output, and I will kindly rewrite this last row to reverse those 2 bits. So this will be then Q0 and carry and sum. And this will be 0, 1, 0, 0, 1, 1, 1, 1, 1, and 1, 0, 0. So as long, so you can see A plus B, right? So 0 plus 0, yeah. And it also like messes up my point. But the carry, since the carry is 1, the carry should also, let's say, stay 1, right? And here we have the same. So these 2 numbers, if carry stays the same, let's say, then A and B is transferred over to the sum. So it is 1. This case is also the same. So A and B plus sum is equal to 1. But we have very big problem if all 3 numbers are ones, right? Because in that case, we have this overflow. And actually, the sum and the carry is equal to 0. So we have a situation where 1 plus 1 plus this carry equals 0. So this is, let's say, what we're trying to avoid. So we can implement this circuit as long as not all three cases are 1. But let's say if this is the case, then we will need to add another multiple controlled X gate in order to, let's say, account for this overflow. So you have to think in advance what number you would like to add, because depending on the size of the number, how many integers how many bits your number requires, and the result, then you should like prepare the correct number of registers beforehand, right? So right now we're, let's say, going back to the era of programming in assembly, when you had to deliberately say and assign memory on a CPU. And here also we have to deliberately say how many qubits we would like to assign for a integer to store. So yeah, let's huh?
You started with the motivation that we have limited number of qubits resources.
Yes.
So we want to compute A plus B and put it back in one of the bits, right? In one of the qubits. But it seems that for that, you already need to add another qubit, at least.
As long as your number you're trying to achieve is less than, in this case, it's less than, it's 1 times 2 times, 1, 2, 4, it's less than 4, I guess. Yeah.
Yeah, but even in the first case, for the one that you started with.
Yeah.
So even here, you have Q0, Q1, and Q2. So you wanted to compute Q0 and Q1 with the purpose, like, and the summation between Q0 and Q1. But for that, you need a second or third qubit. So even for the case that not all of them are 1, you need an extra one.
Yes, I get your point. But let's look that now you can also have this, let's say, carry bit, right? So, so in order to, let's say, maybe for case with 1 bit, it's not that really visible, right? But when you have when you have, let's say, a integer with 2 numbers, let's say 2 qubits, so Q0, Q1, this is for your 1 number, and Q2 and Q3, you have another, let's say, integer, so N1 and N2, then this can be at maximum 3, and this can be also at maximum 3. So if you would like to leave those numbers here and add a second register to 3, then you would need this maybe at most 6. So you would also need 3 qubits, right? Because, well, 2 qubits will only give you count for 0, 1, 2, and 3. Once again, so with 2 qubits, I can have 0, 1, 2, and 3, right? And also here, 1, 2, 0, 1, 2, and 3. And now I'm asking how many qubits I need for this third register to be sure that I have correctly stored those 2 numbers, right? And the answer is that I need at least 3 qubits. Q4, Q5, Q6, right? Because if my maximum number is 6, then yeah, then I need at least 3 qubits to store it. And now you can see that the more numbers you're trying to add, so let's say now let's say with 3 qubits or with 10 qubits, right? The one integer. You also need more and more registers. And now imagine that you would perform hundreds of additions, right? Then you would need 100 more of those registers. But thanks to the in-place multiplication, we can somehow, let's say, cheat and say that, well, okay, we have our qubits and we would like to perform addition, but now maybe I don't need those 3 additional qubits, but I can actually store the result in those, let's say, 3 qubits, right? So after the computation, I will get also Q1, Q2, Q3 with some different values, but now I will call this my register. So yeah, you're right that in the case for, let's say, adding 2-bit numbers, there's not really much of a, let's say, advantage here. But when you increase the number of bits, then you can see the advantage clearly.
Mhm.
I hope that answers your question.
Yeah, thanks.
Yeah. So yeah, so we would like to continue the same. So let's go back to the notebooks. So we would like to perform counting, and for that purpose, we would like, sometimes it's very confusing, so I also need to focus. We will add 2 numbers, so Q0 and Q1, and we will store the output in qubits 2 and Q3, where Q2 is the sum and Q3 is the carry. Yes, perform in-place addition, and first bit represented by Q0, and the output to the output, and then do the same for the start bit in 1. So right now we're a little bit changing perspective. So we are assigning a register 2 and 3 to store our sum, and then we're adding step by step, adding bits, right? So this circuit, when the registers are 2 and 3, this will be our, let's say, register for storing the sum, and we will add 0 and 1. Or yes, so this case, we are adding, as you maybe, if I delete this row, then you can see that this is exactly the circuit we have built earlier, right? So adding 1 bit, and this will be our storage. But if we have 2 qubits, then I have this. This looks like something like this. So yeah, so qubit 2 is in state 0, so we can also omit the first CNOT gate. Yeah, that I don't think that really matters here. So yeah, so now we would like to first add to the sum we added firstly qubit 0, and now we will add qubit 1. So this is exactly, this circuit solves exactly the problem we were trying to solve, right? So first, once again, first adding qubit 0 to the sum register, and then adding qubit 1 also to the sum register. And let's say, I think, no, this is the code to execute and see what is the result. So if both Q0 and Q1 are 0, then we have nothing. If only one of them, then the sum is 1. Remember that, yeah, this is the sum. So 1 plus 0 is also 1, but 1 plus 1 is 2. So 1, 0 in the reverse order. So yeah, now very challenging, I think, task, and implement the procedure, but this time adding the first 3 bits. The sum will be stored in Q3 and Q4. After adding the first 2 bits, it can be the case that Q3 stores 0 and Q4 stores 1, corresponding to the sum 2, 1, 2. From the table, we know that the same implementation idea still works independent of whether Q4 stores 1 or not. So add the first 3 bits, store to qubit 0, 2, and store the sum of on qubits 3 and 4. So basically, you also have to do this scaffolding structure, but now implement this for 3 bits here and 2 qubits. Let's say those 2 sum bits. So yeah, in the meantime, you can start to solve this, and maybe I will draw a circuit you should obtain. That's fine. Okay. Yeah, maybe 2 minutes for you. Solve this. And I can write if you would like to have a hint, then I will draw the correct circuit in the meantime, let's say. So this will be the sum. So first we have double controlled NOT gate, and then single controlled X gate. And again, doing the same for all those circuits. Maybe not the most beautiful drawing, but this is like the scaffold structure that we will then be able to get the sum equals to A plus B plus C. And say in this manner would be that sum equals sum, yeah, depending on what is the first sum, but we assume we start from 0, 0. Sum will be what? Plus, say plus equals A, then plus equals B, and plus equals C. Okay, are you ready? Shall we go through implementation, or you need more time? Yeah, sure. So I will just, for now, copy paste the solution because I already draw it. And let's see if this works. But I will also like to print the circuit. Yeah, so we have the exact scaffolding structure I was talking about. We actually, I think we don't need those additional 3 qubits for now. Yeah, for the circuit 3, 4, so 5 should be enough. Yeah. So let's consider once again. We have input 0, 0, 0, and the output is 0. For 1, 1. We're summing the input is also 1. Now we have 2. Again, should be fine. 1, 0, 0 is 1. Here we have 2 1s, so the sum is 2. Again, 2, the sum is 2. And last but not least, if all 3 are 1s, then the sum, according to this quantum circuit, is also 3. So yeah, we have successfully checked that this algorithm works. And now we will need to generalize it, and this will be quite a task to accomplish, because yeah, so let's review the whole process from the beginning. And with a single input, A, and a single output, B, initially set to 0, we can perform an operation of addition so that B equals B0 plus A. And B can be set at most 1, which, yeah, can be accomplished by a single CX operator. Then we added one more qubit, one more bit, so A1 to the summation. And that, yeah, so after the summation, we have B can be 1 or 0 or 1. If A is equal to 1 and B is equal to 1, then we have an overflow to the next qubit, which will sum be equal to 2. Yeah, we talked about this overflow before. And then we can check this overflow by using double control CNOT gate for A and B when the control B is the target qubit. Yeah, and this is the same half adder as we did before. But similarly, we can also add A2, and if A2 is equal to 1, then the current sum is 1. We have another new overflow, and this time we have to check the sum by applying a triple CNOT gate. So we will check for the 2 1s being in state 1, so this will become 3. So yeah, but so in general, this has, let's say, the following implementation. So first, sum checks for single bit, which is sums the first bit. Then we will need to check if there's an overflow. If so, then apply the overflow. Then check what is the first bit. And again, check if there's an overflow. If yes, then flip the next bit and check and sum the next bit. Yeah, and this is going to be quite a lot of task and quite a hard time to do. I'll just, let's say now, execute the circuit. And yeah, you should see that all those inputs and outputs are summing correctly. We can go step by step through each solution. And yeah, with 4 1s, we have the output of 4. But now what is interesting, that we actually, since after, let's say, 3 bits, we have, let's say, exhausted the number of possible registers, and we have another overflow of this register. We need to add another multiple control NOT gate that will check if all of those inputs are overflow, and if so, then apply a NOT gate and continue with the same implementation as before. Is it more or less clear for you, or not really? So yeah, with this pattern, you have task 3 to solve. And this is, I must admit, quite a challenging task. So now you have 7 bits from Q0 to Q6, and you have to start the result of Q7, Q8, and Q9. And you can do a for loop probably to do this, but maybe 5 minutes, 7 minutes, I don't know. Yeah, you can do it, but it's actually very hard, and I will just show you the implementation after we're done, because It's quite hard. So what I can say for sure, that the first C naught should be like this. Next, the next two should also be like this, the same as here. But starting from qubit 3 and up to qubit 6, you should continue this pattern, maybe 1 minute, maybe not for 8, but 7. You should continue this pattern going down with each qubit being controlled, like down 1. But as you see here, we have the controlled qubit that changes, but the target qubits do not change. So here should be the same. Target qubit do not change, but the controlling qubit change in each step. So yeah, 5 minutes to do that.
May I ask a question, Krzysztof?
Yes, sure.
What is the purpose of this? Because the reason I'm asking is my understanding was, at least now, we will not build a quantum computer which does everything.
Yes.
So there are some tasks that it's easier or better for the normal computers to use, and there are some tasks which are better to be executed on quantum computers. Do we really need to have these summations on the qubits? Can't we just send this part to our calculator?
Yeah, so it turns out that for some problems you actually need those summations. So in general, maybe for, let's say, the most famous short algorithm, this, I think, yeah, addition is also, I think, important. But for this purpose of max-cut problem, we are going to count the number of edges, right? So if we're going to count the number of edges, we somehow need to store the result somewhere. That's why we need addition. And if we add those valid, let's say, edges for the max-cut problem and compare it if it's greater or less than certain number, then we can say that, yeah, this graph can solve max-cut problem with, let's say, 5, let's say, n equal to 1 cut with cutting 5 edges, right?
Yeah, but still,
And
that's the whole point about hybrid computers, right? So do I
no,
need really to do this
You cannot
summation
do
of?
this. No, because if you would, because the whole idea is that you can check all the graphs with different coloring at once in a superposition, right? But if you would like to measure your result and then pass it to classical computer, you would lose the superposition you created in the first place to compute all the different possible outcomes at once.
Okay, maybe
right?
I need to see. Maybe I need to see that, because like the way that I understood
Yeah.
so far is like some summation in between, like a real
Yes.
summation. But like if yeah, so if it's like a one shot.
Yeah. So let's say create a simple problem with maybe not, yeah, 4 edges have to be this one. But let's consider, yeah, once again, a simple graph with, let's say, a discoloring, or maybe this graph. And the question is, how can we color this graph so that the cut is maximized, right, between two different colors. We know this is free, but if those numbers are different, let's say this is qubit 1, Q0, Q1, Q2, and Q3, right? So by doing a Hadamard gate on all of those qubits, we create a superposition of all possible colorings, right? So one coloring, let's say, is red, 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 red. Let's say red somewhere here. Like this, right? Like that, and also here. And let's say 16 cases later, we have, let's say, something like this, okay? But now on a quantum computer, everyone, like all those cases exist simultaneously, right?
Yeah, in one shot.
Yes. So in one shot, I can also, by applying single gate, I can then count the number of edges. And yeah, for this cut, there are no different colorings. Yeah, so this is 0. And for this, I count 1, 0, count 1 and 2, right? And this also is 0. So this counting has to be performed on a quantum computer in order to not lose the superposition. Because if I were to, let's say, measure the state now, I would get only one possible coloring.
One of them, yeah.
And I would have to go in every single step and measure, then count edges, and then go back.
Now I understand the
So
reason.
that doesn't make sense. In order to be superposition to be valid, you have to perform this addition on the computer itself, on the quantum computer itself. And then by doing so, you can actually, let's say, add everything simultaneously, right?
Now this is clear. Now the question is clear. I mean, at least the approach is clear. Sorry.
Yeah.
The approach.
So
okay. Yeah.
One thing I can also say, what we're, let's say, working at FunQubit, is like the assets or the stocks can have can either go up, right, or down. And the question is, what is the distribution? Let's say, you simulate the paths and land here, right? You simulate the path and land somewhere here. And the question is, what distribution of prices can you expect, let's say, 1 year from now, right? Maybe this is, you can expect something like a bell curve, for example, right? Or a log normal distribution. And then based on those all paths simultaneously, you can compute different features. I mean, it's very hard to tell if you not have financial background, but with all those assets and those paths simulated with Hadamard gates, right? You can then perform, let's say, simultaneously at 10, right? Or I don't know, maybe you can do pretty cool stuff with it. Not to mention, let's say, some contracts, but you can create some valuation based on all those different assets and paths at once. Just for curiosity, is it possible to apply the same approach to Rubik's Cube? I don't know, to be honest. It's an interesting idea, really. But yeah, for Rubik's Cube, definitely you have some algorithm, right? Maybe but here, I think in the Rubik's Cube, the idea is different, that we search for operations that will lead to a certain outcome. And here, I think we designed, It's also like kind of operations you design for certain outcome. I'm not sure. I don't will say imagine this Rubik's Cube right now, but yeah, that's interesting idea. So yeah, with this whole topic of, again, why we are adding those gates, I hope that you are able to, in the meantime, create this circuit. And if not, I will post just the solution. And here we do this in a range function. Yeah, here is already initialized. So yeah, we have the first qubit with 0. And something strange here occurs. I will just do this. I know this works. Sorry. I know what is wrong. I haven't initialized the input list, right? So, okay. When I have the input list, then I have this very long string, and fast forward to the last. Let's check if it actually is correct. Yep, so 1, 2, 3, 4, 5, 6, 7 is equal to, the sum is equal to 7. And this is the algorithm once again. So first we only have 1 qubit to check. Then we create an overflow. We now need 2 qubits. So we check for an overflow. If yes, then apply the X gate, add bit 1, and again, do this the same, add bit 1. But now we need 3 qubits. So multiple control X gate. And once again, doing the same for every single qubit. But now, since we have with 3 qubits, you have like 16 possible answers, then yeah, in order to create this overflow, you just need more, you have more space, let's say, to implement those gates. Yeah, and last but not least is number checking. And if we manage to do this, then sure, we can, yeah, this number checking, we can do this. But I think the equality constraints will leave for tomorrow because it's, I think, already late. Yeah, so in order to check a number, we will just simply create a certain multiple controlled CNOT gate, right? So in order to check if a given number is equal to, let's say, 4, we can construct such a circuit. Maybe, let's say, consider each case, right? So in order to check if a number is 1, 2-bit number is 1, we just simply use our flag bit, and we will use simple control NOT gate, right? So this will look something like this. To check if, yes, if this is 1, we can add simply control X gate. To check if this number is 2, so 1, 0, we do the same, but actually take, this is, let's say, Q1, Q0, Q1, I messed it up, but doesn't matter. So the output is 0, 1, 1, right? In this case, should also be 1, 0, and 1. But now we will use the first bit as the controlling bit. Sorry, yes, first qubit as the controlling qubit. Yeah, and likewise, if you would like to check if both numbers, so this is, let's say, 2 and this is 3, if both 2 and 3 are 1s, then we could just simply use a multiply controlled CNOT gate, right? I think this is, let's say, very easy, but this checking for equality will become useful while checking for the inequalities. Yeah, so maybe last one exercise for you is to, yeah, here we have to check for 3. First, we initialize the qubits to set them to 3. and check for free with this multiple control iteration. And maybe last 5 minutes to actually implement algorithm that checks whether the first 3 qubits store the binary representation of number 5. Store the qubit on number, store the qubit on output on qubit 3. So we have, set to 5, 3 qubits, that I mean 0, 1, and 2. And on the 4th, which is indexed as 3, we should check whether is it correct or not. So number 5 should be 1, 0, 1, right? Yes. And we should design a gate that would flag this as 1, 0, 1, and 1. So we can verify this very quickly that this should be just multiple controlled CNOT gate, right? Let's say we can write it as this one, 1, 2, 3, and 4. And we can connect the dots to create something like this. And we will see if this is actually correct. Well, yes, but let's say another solution to this is to also first flip this bit, this middle bit, to 1 with, let's say, an X gate to obtain 1, 1, 1. And then use a multiple controlled CNOT gate. Yeah, there are 2 approaches, but maybe this will be easier for coding. So to apply this X gate to the 0, and this will flag it as 0, 1, 1, 1, and then do the inverse. So apply X gate once again to restore the original value. There are maybe 2 approaches. Probably this second may be easier if we're trying to like automatically code it, so create some if-else statements rather than just using this multiple control. But this is basically equivalent, like this X and using control, right? Should be the same as just skipping this control. It's actually not, because this would also flag
1, 1, 1.
1, 1. Yeah, I was mistaken, right? So this is not the case. We have to use this. Yeah, and the implementation is quite straightforward. I'll just right now copy paste it. And yeah, I think thank you for today, because it's already really late. And tomorrow we will start with this inequality constraint, and also we will switch to Julia, so the new programming language. I thought that might be interesting for you to also learn new programming language. We will continue with this Grover implementation of the MaxCat problem. Do you have any questions for now? If not, then thank you very much for your really kind support and for staying this this long. I hope that you enjoyed today's lecture, and yeah, see you tomorrow.
Thanks.
Thank you, Krzysztof. Thanks, everyone. See you tomorrow.
Thank you. See you tomorrow.
Yeah, thanks a lot.